When you flip a switch, the tungsten filament inside a light bulb goes from room temperature to blindingly hot in a fraction of a second. Maintaining that intense output of light and heat requires a continuous external push, usually from the chemical energy of a battery cell or a wall outlet. This schematic shows the scientific model we use to track that energy flow, a simple closed circuit with a power source driving current through a single resistor. As charges move through the circuit, their electrical potential drops from a higher state to a lower state. Potential energy is simply the stored energy a particle has based on its position in an electric field. In a perfect vacuum, an electron dropping in potential energy would accelerate endlessly, but the electrical current flowing through this wire remains perfectly steady. The steady pace proves these charges are not moving freely. A hidden mechanism inside the wire is actively stripping away their kinetic energy. That energy doesn't disappear. The answer to why these charges don't accelerate infinitely is the exact same friction that makes an electrical device hot to the touch. To see exactly where that energy goes, we have to zoom in past the surface of the copper wire and look into the atomic lattice. Down here, an electric current is not a smooth liquid flow. The electrons violently and repeatedly collide with the heavy fixed ions that make up the metal. This graphic shows a single microscopic collision. When an accelerating electron strikes an ion, its kinetic energy transfers, causing the atom to vibrate. Multiply that by billions of atoms shaking across the material. That mechanical vibration is what we experience as physical heat. Physicists balance this energy ledger. Total energy dissipated as heat over a given time interval equals the current multiplied by the voltage times that duration. When we calculate the energy lost per second, the definition of power, the equation simplifies down to a foundational rule. Power equals current times voltage. We also know from Ohm's law that the voltage across a conductor is equal to its current multiplied by its physical resistance. This equation shows what happens when we combine those principles. The formula becomes power equals current squared times resistance. The heat loss scales with the square of the current. Engineers called this specific heat generation ohmic loss. It is an inescapable physical toll extracted by the structure of the conductor itself. Because ohmic loss scales exponentially, a small increase in current creates a massive spike in heat. At scale, this physical law threatens to derail entire electrical systems. When we zoom back out to the scale of global power distribution, that microscopic math becomes a massive logistical crisis. Power stations are tasked with transmitting immense amounts of electrical power to factories and homes that sit hundreds of miles away. The physical metal in the transmission cables spanning those huge distances contains a significant amount of inherent resistance. If grid operators tried to push a massive electrical current through those cables, the exponential ohmic loss would generate enough heat to melt the lines entirely. This diagram shows the only mathematical loophole. To deliver the exact same amount of total power, engineers must drop the current to a tiny fraction and radically increase the voltage to compensate. Transmitting electricity at enormous, extreme voltages is the only viable method to bypass the square of the current and avoid total grid failure. Direct. That mathematical requirement results in the lethal danger signs plastered across our everyday infrastructure. Those transmission voltages are so deadly that they require massive step-down transformers to manually lower the voltage before the power can safely enter a home. The towering high-voltage grids stretching across the planet are our only engineering solution to outsmart the unbreakable laws of atomic collisions.